Hey there, year 8. I've got a question for exercise 4C, question 3k. So let's just write this up here. Exercise 4C, question 3k and L. I know these two triangles look different to the types of triangles you're used to seeing. So usually the triangles that you often see are something like this, where it's nice and 90 degrees, where this is usually 45 degrees. Then you might get a scalene one as well. So you could get one that looks a bit more like this, like that. And you're still okay with these two because there's a clear vertical height that you're used to seeing, and then you're happy to see a base. And then same thing with this one. There is a height, a clear vertical height that is again 90 degrees to the base, right? But then when it comes to this type of triangle, where technically it's an obtuse angle, you see that when I do it like this now, like that, in this triangle, there's an obtuse angle here. There's no clear vertical height. You almost feel like this needs to be the height that they need to give you, isn't it? A lot of students are hoping to find something like this, but instead, what they give you is they give you a base that looks like from here to here, and then suddenly they give you a height that's like this. And it doesn't feel as intuitive as these two, and whether that actually the formula still applies, that area of a triangle is half times base times height. There is a proof for this, but I don't want to show it in this video to confuse people. So on a quick nutshell, there is a proof for it that it does prove all three of them will still follow this rule, providing one key thing that you need to look out for. The base and the height are always 90 degrees with each other. So you see in all examples, the height and the base are 90 degrees with each other. This is also 90 degrees with each other. And then same thing here, even though you can't see it more obviously, but the height and the base, the height and the base are again 90 degrees with each other. So you still use the same formula despite the triangle looking slightly different. So if you were to do this example here and you copy it down, this line and then this line, they are perpendicular with each other. That's why they drew a little box there. So because they're perpendicular with each other, you can then say area is equal to half times base times height. And once you know which two lengths are perpendicular with each other, it doesn't actually matter which one's base and which one's height. You can call this base if you prefer, or you can call it the height. Really doesn't matter. So here it will be half times 3 times 2, which we know 3 times 2 is 6. So half times 6 there is equal to 3. Don't forget the units. And so it's squared meters. Okay, and then similarly with this example over here, 3L, the area, so you're trying to look for the 90 degrees. So they added on the number 10 to try to confuse you. But again, you're looking for the two sides that are perpendicular with each other. And hopefully you can see 4, if you look at the dotted line, and 3, that's a 90 degree with each other. So when you do the formula again, half times base times height, it should be half, and it doesn't matter which one's base or height. You can then say it's 4 times 3 and not 4 times 10. Okay? And so here we know that 4 times 3 gives me 12, and then half of 12 gives me 6. Don't forget the units, and it's squared kilometers. There you go. So when you're doing this example in your exercise book, please do copy the diagram so that you know for future reference. Have the formula so it reminds you that it's actually the same as every other one. The method, so here's your method. So formula, this is your question with the diagram, and then here's your answer with the units. Check your answers if it's correct, and that's the kind of layout I'm looking for, especially for chapter 4. Okay, so I hope this video helps you to clarify. If you want to look for a proof, there are many already on YouTube. And all you have to type is proof for obtuse triangle. and they'll show you the algebraic proof to it. In a nutshell, if you really want to kind of figure it out yourself, the proof to it is actually using composite shapes. So if you look at this here, try to look at it as the big triangle. See that big triangle? And that's a right angle triangle. And if you minus this right angle triangle in yellow, you will get the area that you want, which is, I'm coloring in pink there. And that's essentially the idea. We can do big triangle minus the small triangle, and you'll see that the formula, no matter what the lengths are, it will always actually end up being half times base times height. That's pretty much the gist of it. But yeah, feel free to look up the proof if you're interested. But I'm not going to show that in this example of this video, because then it will just confuse you. It's just to help you understand that when you see a triangle, it's always going to be half times base times height. The two lengths that you multiply must be 90 degrees with each other, and that's it. Okay?